Assalamu alaikum. Hi, everyone. Welcome to our today webinar, Seismic Interpretation from Principles and Applications. First, I will do 5 minutes presentation about reservoir solutions and our webinar today. First, Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company Sorry for this interruption. So our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researchers for PhD and MSc, assisting in writing technical papers and publish technical petroleum courses by industry, providing mentorship programs, for our upcoming course that is called Practical Seismic Interpretation from Principles to Industry Applications. It is 1 week hands-on workshop using software. For the course is designed for seismic interpreters, geophysicists and geologists, reservoir engineers, postgraduates and senior students, and also seismic data researchers. For the course package, by attending this course, you will enjoy lifetime access to recorded sessions, application datasets, application-based workshop, course material also will be provided, open discussion with the instructor during and also after the course, and you will have a certificate with online identification ID. By the end of it, you will be able to understand the fundamentals and theory of seismic interpretation, apply the industry practices in seismic interpretation, load 2D and 3D seismic data on software and QC it, do seismic to well tie, use horizon and time slices and flattening seismic cubes, pick horizons, felt sticks and fault polygons, generate structure and isochore maps, make velocity modeling and time to depth conversion, understand seismic attributes, definitions, classification, use structure and stratigraphic attributes, and also blend multi-attributes. For the course content, I will send the link for course content on the Zoom chat to be review the daily content. For our today webinar, the instructor for our today webinar is Dr. Ahmad Saeed Ali. Dr. Ahmad Saeed Ali received PSc at 2007 and master degree at 2015 in geophysics and PhD in exploration geophysics at 2021 from Al-Azhar University. He joined the Karun Petroleum Company in 2008 as development geophysicist and specialized in seismic interpretation, seismic inversion, and reservoir characterization. His professional interests include interpretation of seismic data and reservoir geophysics. For his PhD dissertation, he was working on prediction of reservoir properties and fluid using rock physics techniques. For our webinar today, the rules, please, if you have any questions, you can ask your question into the Zoom chat. Please mute your microphone and camera. Also, fill into the form sent into the chat to get a webinar certificate. So again, if you wanted to have a certificate of attendance for our webinar, you should fill into the form that will be sent into the Zoom chat. For upcoming webinars and courses, you can join our Telegram channel and also our social media platforms. Contact us through our mail and the WhatsApp that also will be sent into the Zoom channel. Thank you all, and Dr. Ahmed, you can start now.
Okay, good evening, everyone. Let me share my screen. Okay, I hope my voice is good and the screen is appeared in front of you. Do you hear me? Inja Abdallah, is it okay? I want to make sure you hear my voice. Hello? I want to make sure that you are hearing my voice.
Yes, we can hear you.
Okay, let's start. Good evening, everyone. Today we are going to talk about the seismic interpretation principles and applications, and the factors that affect of your seismic data during your work, and the agenda that we are talking about. We're going through this agenda, the role of seismic methods in exploration. Then we'll move to the exploration workflow and the role of seismic data in this workflow, and the acquisition-related factors affecting seismic data, then the processing-related factor affecting your seismic data. Then we'll talk about the seismic components like wavelet, frequency. Then we'll move to seismic attributes, and then the resolution of seismic data, and then a practical workflow. Starting with the talking about the oil field life cycle, we have three phases. The first phase is the exploration phase, then the appraisal and the development. The exploration phase is the first phase, and this is very important phase that you should prepare yourself for this. And in this phase, you should find the oil and gas pools, and you should find where the regions and basins that you should searching for your oil and gas in, and which blocks inside these basins. Of course, the seismic data represent the aerial extension, cover an aerial extension of wide range of area. It's like the seismic data and well data is very major to use this, very common in the oil industry, seismic and well log data. And of course, the well log data provide you the direct downhole measurement of properties and other geological attributes. But although logs provide a relative high resolution information, this information is specific to the well bore. So the lateral variation of the subsurface characteristics may be you cannot find this, or you cannot characterize this in the distance between the wells by using the only the well data, and this distance may be reached to hundreds or thousands of feet or meters. So the seismic data provide you with the continuous and the cover this extent of this area, and enable you to identify the structure or subsurface structures that are in your the subsurface structure that appear inside your area of exploration. Of course, it have a scale and a limit of resolution.
Dr. Ahmed, please, sorry for the interruption. If you can, if you have 2 monitors, please put the zoom onto the other monitor, because
yeah.
from the display setting from the above.
Oh yes, okay. I shared the other screen. Mm-hmm. Okay, start to. I can't find this. Okay, I can disable the.
Yes, you can. You can display it, and then from the display setting.
The display setting,
you can press slideshow. Okay.
Oh yeah. Okay. I think now you have.
You can press slideshow.
I want to make sure that you have the.
Or you can
share is stopped.
F5.
Share. Now you have the screen.
Yes, you can press F5. Yes, F5.
Now you have the view.
Then you
screen.
Display setting into the yes.
Now you have the.
Yes. It's a great now. Yeah.
Okay.
Thank you.
Okay, let's continue. So in exploration phase, we have we should have the opportunity to find the major gas pools. So the seismic data is a method that used to identify these pools, and this data may cover a wide range of like more 2 or 3 basins. So you have regional data that cover the basins, and you should find your oil and gas inside one of them. Then you move to from the exploration. If you succeed on this stage, then you move to the appraisal. And the appraisal phase, you should find to what extent the reservoir is extended in your area. And then after that, you move to the development phase. And in the development phase, you should find this in a small details. You are working on the small details. So the seismic play a role in actually in the three phases: the exploration, appraisal, and development. And the question that you should answer is, do you have which basin you have? You will find the oil and gas in, and if you find the oil and gas in this basin, which blocks you have more blocks in the basins. So have more blocks. Which block you can find it, and what is the charge, or the charge arrived here, or you have a structural traps there. So, and where in this inside the block itself, you find the trap for your hydrocarbon. What should you expect from your well? What about the volumetrics? You have enough volumetrics and you have enough oil in order to have the economics. So the economics play an important role in your in the industry. Will if you have a good reservoir and you have a good trap and don't have enough you do not have enough oil and gas or hydrocarbon in general. So why you will drill your well? So this is these questions are the very principal questions you should answer, and the seismic will help you to answer these questions. And the ultimate goal for the exploration is to answer this question that we said: where to drill, the location of the trap that you will drill, and then the depth. To which depths you should find your hydrocarbon. The second question is what to expect. What is the volume of the hydrocarbon? You have a good volume of hydrocarbon or not? If you have good, or you have multi traps, so you have to rank your traps according to the volumes, and of course, and risks. And the third question is how certain is it what is the chance of success? You have a risk here. Of course, we have a risk because we have an uncertainty in our data. We have an uncertainty in resolution. We have an uncertainty in the tools. So the certainty play an important role in our industry. And the last question is how profitable is it? Is it a good in economics or not? So seismic will help to identify or help you to answer these four questions. And if you look at the petroleum system elements, which is this is the most important thing in industry, you have to find your petroleum system elements and identify these elements. Call this the first one of these elements is the source. You have a source circ. If you have a source circ in your area, and this is the source circ are inside the oil and the oil window, or inside the gas window, in order to have enough temperature and pressure in order to generate the oil or not. Then you should have the reservoir distribution along your area. You have a good reservoir, okay, I have a good reservoir, and this reservoir have your do you have a trap that entrap the reservoir and could entrap the oil inside this reservoir or not? And of course, the migration pathway. And this, if you look at this section, this is a cross section. The cross section shows you we have the multi-depth, or you have a basin, and this basin we have a lot of structure outside the basin, which area we can drill, which trap we can use to identify our hydrocarbon, and where is the gas, where is the oil. If I have a facility for gas, or I have a facility for oil, and I'm looking for I'm looking for an oil now because I have a facility for oil only. So where should I drill? I drill near to the basin or away from the basin? All of this we cannot know all of this information when we are walking on the surface. All of this information are subsurface information. And the subsurface information we cannot get without acquiring seismic data. Seismic data will help to identify all of this the subsurface structure. Of course, the subsurface structures will yield the elevations, and then we will identify. We can identify where is the deepest point and where is the deepest point in the source rock. Enter the oil window, gas window, or the migration happened, and which way of the migration. And do you search in the right block, or you are in the another side and you do not have a migration pathway there? All of these we can identify by using the seismic data. So seismic data is very important, the oil industry, and we are using this for a long time. And we are started with the industry started by using the 2D seismic data at the first. Then then they moved to the 3D seismic data, which provide a good resolution, of a good resolution better than the 2D seismic data. And then after that, the 4D seismic appears, and then 3C and so on. In order to identify our seismic data role in exploration, we will talk about the exploration workflow. The exploration workflow starts from capturing an area of interest. The area of interest you are capture, you can use it the gravity or magnetic in order to identify a smaller area to acquire your seismic data. Then you again acquire your seismic and the in seismic acquisition process. In the seismic acquisition process, you are acquiring the data. Then you have a data, and this data and we are taking this data in order to process this data and get a good interpret a good picture or a good subsurface imaging for structure. The seismic data interpretation, this is the third part in the seismic process as a whole, and this is a very important step. And of course, we have a lot of things that affect the seismic data interpretation in the last two steps, which is the seismic data acquisition, seismic data processing. And each interpreter should have an overview of seismic acquisition and processing in order to have a good interpretation and good structure identification and prospect generation. Then you assess your prospect, and this based on the seismic data you have, the seismic data you got. You have the assess your prospect, and you assess you have the volumetrics, and is it good or not? Is it economic or not? After that, you are trying to rank this prospect according to all the information you have got from the seismic data. Then you drill your wild or exploratory well. Till now, we're using the seismic data, starting from seismic data acquisition till this step. We have the seismic data, because you do not have any drill well in your area, so you are depend on the seismic, and you're trying to find a wildcat in order to get a lot of information from it, or an exploratory well. If you have a nearby block that have a drilled well, then you move. If you have a failure, okay, you are re-evaluation your the steps that you are follow. Then if you have a success, you are try to move to the appraisal phase. Then if you have a success, you move to the field development. And actually, the seismic, as we said before, seismic starts from the seismic data acquisition till the field development. We cannot leave the seismic, and cannot use the well logs itself, and cannot use, of course, the seismic itself. It should be an integration from using seismic and well data. And as the ultimate goal of the seismic is to find the subsurface structure in order to drill your well. And the 3D seismic data you have in your area, you may have a lot of targets, you may have multi-targets, and you should take in your consideration these targets and the depths of these targets. Where is this targets, and I am the primary target where, in order to design your frequency and acquisition, the acquisition parameters that will help you to identify this structure in a good and increase your noise, increase your signal to noise ratio. And in seismic, in brief, the seismic data, we have used a source of waves. This source of waves transmit the waves inside the earth. And this is the waves come to the interface between two layers, and you have these two layers have difference in the density and property, and density and velocity. So if you have a density velocity contrast between the two layers, the waves reflect, a part of this wave reflect and come back to the surface, and we record these waves. Then after we record these waves, we are trying to move to another location in order to generate seismic pulse, and then the seismic reflected. Then we record this seismic. After that, we take this seismic data we have the seismic data in the field, that in the right, in the left, the seismic data here. We have this shape in the seismic data in the field. Then we are processing the seismic in order to come up with this full image of seismic, in order to have the obvious or clear picture of structure that we can pick and trace these faults and trade the reservoir, wherever the reservoir were. Then we are trying to find a good structure trap after the interpretation, to find the interpretation and find come up with a structure map which have show us the location of the beast location for drilling well. We have here a trap, another trap. So we are talking about the traps, then the volumetrics, and we cannot measure these traps or come up with this structure map without starting with the interpretation. And the interpretation yield this map, and we can calculate the volumetrics, and we have this area, and we can, from the seismic, calculating the thickness, and come up with the volumetrics that we will use to document this information before drilling our well. Of course, these three steps of seismic acquisition, processing, and interpretation have a lot of steps inside each one of these. So in the acquisition, we have a lot of factors affecting seismic data. These factors that affect the seismic data, of course, will be reflected in the interpretation step. The section of the interpretation of the seismic data, or the volume of seismic data that will be produced from the processing, of course, will be affected by the the first two steps, the seismic acquisition step and the processing step. So it's very important to take care and to know what is the pitfall that we should or that we may face in the acquisition and processing, in order to know, is it in the seismic interpretation, is it good, or is it in the seismic interpretation, is it real or not? Like this feature, is it a real feature or not, or this is maybe affected by from the processing, or maybe affected by the acquisition of core itself. Of course, we have a lot of things that may affect the seismic in the acquisition and processing, and the good interpreter should have a good eyes in the interpretation, and should have a good information about the acquisition and processing, in order to eliminate the possible pitfall that may be happen in the acquisition or processing. So we'll talk about some factors that affecting the data in the acquisition that may affect your seismic data. If we started from the acquisition itself, the design of the survey itself may have an impact on the seismic data. You have the seismic data in 2 dimensions. You are acquiring a 2D seismic data. Of course, you have the source. You should have the source, and you have a receivers in order to generate the pulses, and pulses go through the ears, then it will reflect at the interface, the first interface. It will reflect, then come back to the receivers, and we record this. Of course, the parameters of the receiver itself have an impact on the seismic data. You have the interval. You have this. If you have the receiver interval is 50 meters, you have the subsurface coverage will be the half of this distance. So the farthest offset should be at least the twice of the depths. So if you have if you have your main target at the depth of 1 kilometer, the farthest offset should be 2 kilometer. Okay, and cannot be exceeded for twice this distance. And this is very important to know before acquiring your seismic data. Where is the target? Where is the main target? Of course, you have a lot of targets. You may have a primary and secondary target, but the primary target, if you are targeting in your area, you should have the depths, or you have a range of the depths, so you can acquire your seismic data and design your survey in order to have a good parameter that will reflect on your seismic data. And then in the 3D, in the planning of the 3D and design of that 3D, it will be more different of the 2D, but you have here a bin size. And this is the bin size is the bin size, this is a square. You can imagine that is a subsurface square, and subsurface square have a dimension, and this dimension controlled by the receiver spacing on the surface. If you have the receiver spacing at 50 meters, the dimension of the bin will be 25 by 25 meter. So this is very important because if you have a feature in your area, you have a forest, or you have a channel, stratigraphic trap, like a channel, and this have the width of this feature you are trying to capture is 20 meter. So if it was a 20 meter and you design your survey the receiver spacing parameters to be 50 meter, you cannot image your subsurface, and you cannot image your target or the forest or the structure feature that you are trying to get, or the stratigraphic feature you are trying to capture. So it's very important to know your area and what is the geology of your area before designing your survey. And if you are acquiring your seismic data and you do not have this information, when you are trying to pick the reservoir at somewhere, you will not find your reservoir. You cannot find it on the seismic. Of course, it's present in the subsurface, but you cannot find it in some areas. And some areas you can follow the seismic in order to define the forest. So you have a forest, you have a good structure, you have a forest, or you have a channel, but in some area the width of the channel become less. So you cannot trace your channel at this area. So you may fail in your mission in drilling the well, and you have a failure. So the very important, the receiver spacing, the very, very important in the acquisition. This is an example from the acquisition. Another example or another factor that may affect your data, when you are acquiring the seismic data, you have a source in your surface. Then you are acquiring the source and generating a pulse. The pulse go in the earth, then it reflect on part of this energy reflect on the first reflector, then come back to the receiver, and then we are recording this. And you have then you move your source, then acquiring the generating pulse, then recording this pulse, uh, changing your position, generating also in order to capture this. Of course, in eliminating all the other points, we are looking on this midpoint. On this midpoint, you have a multi-reflections that recorded by multi-receivers and multi-source points. And this called this in here in this example, it's repeated 4 times, and we can call this default. This is known by default number. Default number is the number or the time that you image your point and record the data that comes from this point in your recorder. So this default number is very, very important. Of course, you have a high fold number, you have a good image. Low fold number, low image. And this is very, very important in the quality of your data. And this is an example for the data that you can get from the fold number or 15-fold number at the left, then 30-fold number on this in the middle, and 60-fold number on this. So this seismic generated from 60-fold number. Of course, you can reach for 96 and 120-fold number. And this is the only difference in this section. This is the fold number. So you have here the if you have your reservoir in this interval, you have the reservoir in this interval. This interval may be captured good here in the 60-fold by 60-fold number, and maybe it's poor here in the 15-fold number. So fold number is very important in imaging your area. You cannot control the area of our trap here. We cannot control where is the extension of this trap. Is it can be extended here, or we have a discontinuity here and we have a structure here, or we have a continuity and we have all the reservoir continuous to all this point and maybe beyond this. This is very important question, and these questions we cannot answer without looking at the stacking fault. And if we move to the fold coverage, this fold number, we can express this fold coverage by the mapping of the fold number map. The fold map showing you in color here the number of fold that every single point have been recorded by. So we can refer to the fold like with the nominal fold, and the nominal fold is the number of time of folds that we design our survey to capture 96 fold number. So the fold number here is a nominal fold. And looking at this line, the red line, of course, the red line expresses the high fold number in this area. But this because we are covering this area more than the other areas around this. So if you have your seismic data and you have a good fold number and you have this anomaly, if you're running seismic attributes on your data, if you have this still in your data and you cannot eliminate, if you cannot eliminate this and you are running the seismic attributes in your final seismic cube, you will find an anomaly, and you will refer to this anomaly, may refer to a geological feature, but in reality, it is not a real, because this is a fold number that the anomaly comes from the covering this area more than the outside, the surrounding area. So take care on this point also when you are acquiring your seismic data. Other thing may you have found in the data or in the acquisition that may the factor that may affect your data. You have we have here an image for the subsalt, and these subsalt are imaged using the seismic, the wide azimuth, and the conventional seismic are in the to the left, and the wide azimuth to the right. The wide azimuth, of course, have a good impact on the seismic, and we have a good definition of the subsalt. And you are looking at this on the left. You have the reflections here. We cannot tracing the reflections in this area, but in the area on the right, we can go through this, and of course we can extend the interpretation in order to find the traps which could be here, because we have a salt body here, and this may be a good stratigraphic traps. So we cannot image this. We image this area, but we cannot find a good parameter that could help us in the acquisition, that could give rise these horizons to be occurred here in the data. So the azimuth itself playing a good role in the imaging the data and the quality of the image data. Another example, for the azimuth, we have you have this circle here, and we have a lot of angles. So we have angle 2 and angle 5. This is the angle 5, and this is the azimuth of angle 2. So you are imaged your data in two azimuths. You are in this direction and the other direction. So if you are imaged in this direction, you got this image. But if you image your data using this direction, you got this image. And look at this circle, the blue circle. You have here a good image in azimuth using the azimuth 5. On the other side, you do not have a good image here. Also, you have a good reflectors here, the azimuth 2, but you do not have these good reflectors here. So you cannot capture the all information using one azimuth or the azimuth 2 or azimuth 5. So maybe you use a combination of azimuth or full azimuth acquisition to provide a good opportunity for optimizing a good velocity model, which help you to build a good structure complexity or a good structure complexity settings. Another example, using the tool of the acquisition itself. When you are acquiring the seismic data, offshore seismic data, you have the opportunity to use the ocean bottom cable, or using the ocean bottom cable or the streamer. The streamers are towed beside a huge ship, and the ocean bottom cable. These cables, ocean bottom cables, we can put these cables on the bottom of the sea. So you have the opportunity to capture all the data, and you have a short distance that the reflected seismic waves will be recorded on the bottom cable, and the seismic data will have a long distance to reach from the seafloor to the streamers on the sea level. So they maybe affect your seismic data, and you have an example that may show you that the effect of using streamer and ocean bottom cable for the same area. We have here a good reflector that maybe we have a good continuity here. We can continue and tracing our reservoir like this in this area, but using the streamer, the conventional way of acquiring seismic data, we cannot know if this reflector here continuity or have a continuity here or have a structure here. We have a good fault here. So this is the upstream side. This is the downstream side. So this is very confused. to interpret this area. But when you see the ocean bottom cable results, okay, of course, this is very, very important, and it's very, very clear that we have a good continuity here, and we do not have here a structure. So this is this is dependent on the tool that you use in the seismic acquisition. Also, the geometry of seismic data playing a role, playing an important role in showing your results of the seismic data. If you have used the two spread designs of the seismic acquisition may yield a different picture. We have here two examples from the same area that was covered by using the block array, block geometry, and we have here another geometry. This is a cross spread geometry, and this is brick geometry. So we have here an amplitude in the upper left side. We have here a good amplitude here. We can notice that we have here a good amplitude, but we do not have this amplitude here. So this is it's yield two different pictures. Also, the structure of the area, the faults that may be clearly identified using this volume. And we can identify the faults here, but not clear like this image. So the geometry have an effect on the seismic data. All of the mentioned examples were examples that was depending on the acquisition or during the acquisition. So we have a lot of factors that may affect the data that we have in our hand, but we cannot know what happened in this data and what affected this data. We cannot refer this anomaly absence here to the presence or absence of hydrocarbon. If you are trying to integrate this data and you are looking to these data sets, you may refer that we do not have here a higher amplitude because we do not have a gas sand. And we have here a higher amplitude because we have a gas sand. At the first look, at the first glance, at a glance, you can see that we have here a 4D seismic, and this is the old, and this is the recent, but this is not the real. The real is that we have used two different geometry in applying our seismic data. So it's very, very important to read your report, the acquisition report, before starting the interpretation, in order to know which problems happened during the acquisition and what the steps that have been taken in order to overcome this. And of course, this may help you in your interpretation and may help you in introducing a good interpretation and identifying a good prospect. The second part is the seismic processing related factors that affecting the seismic data. The processing related factors that may affect your seismic data, we have the most crucial thing in the seismic, which is the velocity. The velocity may yield a lot of problems in the area and during the processing of your seismic data, and this may be happen as a result of the presence of a weathered layer. This weathered layer may have a different thickness, or you have a different erosion, differential erosion. Differential erosion may cause a lot of problems in your area during the processing, because you have a lot of a velocity differentiation from here to there. We have here a weathered layer, but we have a thickness of weathering here, differ from this thickness of weathering, another different thickness, another thickness. So this may affect all the data below the weathered layer, and all the data below the weathered layer are affected by this and may yield a false structure, which lead to drilling a prospect that appear in front of you at the prospect, and you have may have a four-way deep closure, and after you drill the well, you may find this async line. Yeah, of course, you can find this async line, and you can, or may you find it a four-way, but you do not have the closure height that you are find on your seismic data. So the economics will change, and it's very important thing in the processing, the velocity issue. And this may happen, of course, the processing trying to eliminate these effects, but we are trying to reduce, not eliminate. The precise word is to decrease the effect of this, not eliminate the effect. We cannot eliminate any effect. We are trying to reduce as we can. So the processing trying to eliminate all of these effects and yields a good subsurface image. Of course, the BSTM differ than BSDM. The BSTM, the pre-stack time migration, differ than the pre-stack depth migration in imaging the subsurface. And the pre-stack depth migration yields a good picture rather than the BSTM. And the BSDM, the cost of the BSDM, the very high, the higher than the BSTM, and of course take more time. So when you are dealing with BSTM data and BSDM data, you will find a lot of differences in your area if you have a lot of opportunities to have these differences, like a differential erosion or a weathering layer. So take care in your interpretation when you are dealing with a BSTM, because the BSTM cannot deal with the lateral variation of the velocity. Otherwise, the BSDM can deal with the lateral variation of the velocity. So it's very important to know which version of seismic data you are using. You are using the seismic data in time domain, the time domain data. Okay, the time domain data, this data time domain and BSTM data, or a BSDM and in time domain, BSDM converted to time. It's very crucial to determine the data. It's not necessary to you have a BSTM data to be in time domain. You can have a BSDM data, pre-stack depth migration data in time domain. So the version is very important, not only the domain of the data. No, you have to find the version of your data before you start the interpretation. And this is a very crucial step and may yield a structure different than another cube. Another thing that may affect your data in processing that could be the effect of the stacking or the residual stacking. When you have your traces, of course, when you have a different offset, so you have a lot of differences in your reflector. The data that you have here, if you have the data, if you have this section, this example, the example A to the left, we have here a stack. We have this section before stacking, and after we stack this section, we may have this picture, and this is not the real. And the real picture is this. So this resulted from the improper condition of the data. We have here, we should have all of this reflector at the same level, but as a result of the conditioning of this data or on or applying the improper static correction may yield this picture. And when you are stacking your data, you have this, and of course you do not have this in reality. You have this in reality. So this is express the subsurface and the interface, and this express about another interface, but we have this is in real. So the static correction is very, very important. Even if this data, even this data have been affected, this data have been applied, the static correction have been applied to this data, but still we have a residual static need to be corrected. And when you try to trying to remove these residuals, of course you will get a good picture. Of course, and this is the role of the seismic processor. But as an interpreter, you do not in another room and the seismic processor in the other room. No, you should have a good connection, a good communication with the seismic processor, and during the processing steps, you should be present, and you should be present in the processing center and continue to find the data and the problems that they may have and they may face in the data. Of course, you have a lot of milestones and a good you have a lot of milestones and certain points you should have a decision, but all the ways and all times you should have a good connection, a good communication with the seismic image processor in order to overcome this and trying to get the benefits from the data that you paid a lot of money to get. After we talked about the main factors that affecting the data in acquisition and processing steps, of course we have the data that we are dealing with. The data you are dealing with that you got from the processing have a lot of types or dimensions. You have 2D seismic data, we have 1D seismic data, 2D, 3D, and 4D. And in this example, we have here the 1D is expressing the BSP data, which recorded inside the well after you drilling the well. We have to find a relation between the depths that you have found the formation inside the well and the time that the waves take in order to move from here to this formation. So we have a relation between time and depth. Then we can use it in our data in interpretation. Okay, and the second type of the data is the 2D seismic data. And in this data, you have a two-dimension. You have covering a two-dimension of the seismic data. The two-dimension of seismic data is here in our example the x, then the z, the z, then the x or y direction. This is a one dimension of seismic. This is two dimension of seismic data. Another dimension is a 3D dimension seismic data, or what we call 3D seismic data. It give you an image or a volume of data because it image in the direction of the x, the direction of y, and the direction of z. So we have here x, y, z. Then you come up with a volume of data that including all the point here are recorded. We have all of these points are recorded here. But in 2D data, we have this section only that recorded in our data. So we have a good coverage here in the 3D, and we do not have good coverage here. We have a single line here only. In the 4D seismic data, we have the same area. We record the 3D seismic in the data in our area. Then after time, we are acquiring the same survey with the same parameters for the same area, same area, same parameter, same field with all the data, with all the location of receivers and the parameters of the receiver GPhones, all parameters the same. But we have here the time difference. This is the example from was acquired, the area was acquired in 1985. This is in 1999. And this area here, we have here, this is the schematic geological section or cross section for the area. This is in the Gulf X field. We have here and in 1985, we have here oil. Then we have the aquifer. We have here a water. Look at the seismic here. This is express all of these features. We have here, this is the top of our reservoir. So we have here the fault. Then we have here all of this is inside the water, and this is our reservoir and our trap. After producing from this area, from well A, then of course the water will rise. So after the water is raised, the water here, after we are acquiring the seismic data in 1999, the data here affected by this, and it express the presence of oil. So the presence of oil was limited here in this area. So you are looking at the bright amplitude here in the seismic, which represent the difference between the density contrast between the non-reservoir and the reservoir. So we have here this bright spot, this bright amplitude are limited to this area. And the first acquisition was all of this area have the bright amplitude, which express that we have here a reservoir for us. So this is a good reservoir here, extended reservoir. After reducing from it, it becomes here for this. So the 4D help you to identify where the oil water contact were reached and where your reservoir becomes and the volumetrics that remain in your area. The seismic data dimension or 2D, the seismic data is 1D, 2D, 3D, or 4D. All of the data are recorded by using a theory of convolution. The theory of convolution that suppose that you have a geologic column of shale, sand, and another maybe granite or another igneous rocks. Then you have an acoustic impedance, and this acoustic impedance is a density multiplied by velocity of the layer. So we have here a good have an acoustic impedance here for this layer, which of course differ from this layer because there's different lithology, different density, different velocity. So we have different acoustic impedance, or then different acoustic impedance, different acoustic impedance. Then this acoustic impedance we are calculating from this acoustic impedance RC, reflection coefficient, and this express the quantity of the reflected waves to the quantity of the incident waves. So we have here a reflectivity here, and there are reflection coefficient. By calculating reflection coefficient using the RC law, which is Z2 minus Z1 over Z2 plus Z1. We are getting with the RC this, then all of these steps, the two steps are a theoretical steps, or this is found in the subsurface. We cannot see this RC or acoustic impedance in seismic. We cannot see this without acquiring seismic, because the seismic are sending this wavelet, which is the seismic acquisition process. We are sending a wave. So this wave, we are here using the wavelet. The wavelet here, like this is the seismic acquisition. Then the wavelet come here, and the signal go through the earth, then convolved with the RC in order to give us the image or the subsurface image of the reflectors, different reflectors. when this convolved with the first RC give us this peak, then when reflected, the seismic waves reflected, then we are recording this, then the other part of the seismic waves transmitted to the another surface, and then to image the second surface, which will be the trough. Then we have a bigger trough, then we have a smaller peak, and then we come up with the collective response of all of these peaks and troughs, which is a seismic trace. So the collective response is this seismic trace. So we have here a lot of responses that we are sum. This is a summation, the mathematical summation of this, which give us the seismic trace. The seismic trace here affected by all of this. So we have a lot of things in the seismic that control the peak and trough, and how much the bigger the peak is big, and how much the trough is big. So all of this affecting the seismic data, and of course limiting the resolution or increasing the resolution of seismic data. And talking about the polarity of the wave, which why this reflector give us a peak and the others give us a trough. Of course, this is because we are using a type of polarity definition, which may differ between the companies itself. So it's very important to know the polarity of your data before you start the interpretation, because you may have a data that farmed out from another company, and you have two different seismic cubes. Two different seismic cubes for two adjacent areas, two adjacent blocks, and you are started the interpretation on the first cube. Then you reach it to the start of the second cube, but you find that you have started the interpretation on a peak. Then on the other cube, you find it a trough. So you may think for the first while that this is a shift. No, it's not. Maybe not a shift. Maybe a different polarity cubes. This may lead to the different interpretation and different results, especially if you are running a seismic attributes or you are dealing with a seismic inversion. This may lead you to trace another reservoir, and you do not have the right picture for your reservoir. So the polarity is very important to know. We have two types of polarity: the positive polarity and negative polarity. The positive polarity, that if you are convolved with this case, we have here a hard kick. You are moving from a soft like sand to hard like limestone or like a limestone. So you have a different density and velocity. You have here in the hard the limestone case, you have a density, high density and high velocity. We have here a low density, low velocity. So we have a big difference in the acoustic impedance. Here, acoustic impedance is very big. So if you are multiplying your data with using the positive polarity data, you will get a peak. So we'll express this interface as a peak. But if you multiplied your data by using a negative polarity, you will get a trough. So big difference if you have a peak or trough using your seismic data. It's very important to know this is an American polarity and this is European polarity. But it's a very confusion. It caused a very confusion for geophysicists that work in the oil and gas industry. But the simple thing is to know your polarity and ask. Do not ask about is it a positive or negative, because this is a positive polarity for the American polarity. And when we move to the European polarity, they consider this a positive polarity. This is a negative SEG polarity, but you are trying to know, is it a positive or negative? So you may fail in asking this question to to another one in American company saying this is a positive or negative, he will answer you it's a positive from his point of view, but it's a positive from your point of view, different than the positive for his point of view. So trying to ask a simple question. The simple question is the increase in the acoustic impedance are expressed by peak or trough. This is the very simple question and will prevent any confusion to take place with you and your data. Another important thing, the phase of your data. The phase of the seismic data that you are using may lead you to have a problem in your data and may you fail in interpreting your data, because the phase may differ, may give you another picture for your reservoir. And in order to understand the effect of angle or phase angle on your data, we will move to the next phase, next slide. And this is the minimum phase data. The minimum phase data, when we are linked to the geology, we have here two different layers. First, the first layer, and this is the second layer, and this is the interface. If your data is a minimum phase data, you should find the geological top, the top of geology here. And if you are trying to pick your seismic data here, and this is very easy to all interpreters to pick the data inside the peak or inside the trough, you will fail to find your reservoir. You will trace another place in your reservoir, and maybe you miss your reservoir and hydrocarbon potentiality. If you have a potentiality in your top of the reservoir, and you are trying and you are picked this part, you will miss your reservoir here. So it's very important to know, do you use a minimum phase data or zero phase data? This is the difference between minimum phase, and this is the zero phase data. Of course, very big difference. The zero phase data here represent the zero phase data here, and the maximum amplitude of the reflector represent the same top of geology. So if you are trying to pick on your seismic data here, the top of the geology here, and you are trying to extract seismic attributes, you will have sorry, you will have a good picture for the reservoir and the distribution of your reservoir, a real distribution for your reservoir, and you will not miss any part of your reservoir. So it's very important. This is the zero phase and this minimum phase, zero and minimum phase. Very big difference to know the type of pulse that you are using in your seismic data. And all of these aspects, of course, we have a lot of things that play an important role in seismic data and imaging the seismic and the result of the seismic cube that you got, like the frequency and a lot of things. And the most important, the frequency also, like the wavelet. And all of this, we are taking care of these things in order to have a good picture of the subsurface or a good image of subsurface. And we have two types of subsurface images that we can get. We can image the subsurface in order to, if you have our area are affected by structures, and we have a lot of structures, we can have good image represent the subsurface structures that are present in your area. Or maybe you are dealing with another area that have a lot of stratigraphic features that you're trying to capture, like this area. You have a slope, you have a shoreline, coastal plain, slope, and floor fan, basin floor fan. You have a lot of settings that may be captured by the other one line or cannot be captured by one line. Of course, the very mega scale. So you are trying to dealing with a data, and this data have uncertainty. The uncertainty of your data should be taken in your consideration in order to know the impact of this parameters on your interpretation and your data. You are trying to interpret the data in terms of stratigraphy or in terms of structure. So it's very important to know the factors affecting your data. Of course, the seismic data have we have a lot, in seismic data we have a lot of reflectors that appear here in this example. We have a lot of reflectors, and of course we have one reflector represent the seismic represent the top of our reservoir. So the top of our reservoir may have here picked in the seismic data. We have our reservoir, maybe this top, then we have a fault, then we are continue to trying to find our top of the reservoir. We have a good trap here, against default here. So this will yield this interpretation will yield a structure map that represent the trap of the seismic. The trap of our represent the trap of our hydrocarbon. But we are using here only the interpretation of the beacon trough to find the place of the trap. But we have a lot of information. We have an amplitude, we have a frequency, we have a lot of things that may affect the seismic data, may be included in the data, inside the data, not only picking the reflector that will yield the map that we are need. But of course, we have a more data, more information inside the loop or inside the reflector. And of course, the seismic attributes trying to find that hidden information inside the seismic reflector. The hidden information inside this reflector can be extracted from seismic using seismic attributes. And seismic attributes trying to extract some information regarding the time, amplitude, frequency, and attenuation and phase. All of this information are helping us in identifying data, identifying our reservoir, the faults and the structure that we have in our area, and the geometry and the fault trends, and a lot of things that we included in our area. And this is an example of seismic attributes that we have on the left side is the seismic data itself, and on the right side a seismic attribute, which is a coherency. The coherency yields a lot of the information that we cannot find or cannot find it clear on the seismic data. We have here the fault, but we cannot find this fault. We cannot identify this fault clearly here. A lot of faults here. We have a faults here, there, but we cannot find it clearly here on our data. Moving to another example, we have here we have a lot of channels, and this cannot be yields from the seismic, but we are trying to use the seismic attributes. This is a horizon slice for the seismic. This is a horizon slice for the data that we have. Then moving to another slice, which is a slice for a frequency amplitude for a certain frequency, which is a 16 hertz, yields these features better than the last slide. And here we can identify a lot of features in this slide better than this previous slide. Then if we are using another frequency, we can find a lot of things. We are using 26 hertz to extract an information from the seismic tube and identifying a lot of things of our data. We have here a difference between that 16 hertz and this 26 hertz. A lot of differences we have here. The channel are obvious here in 16, but we do not have it here. But we have another point here appeared in 26 frequency. So we are using this data. We have a lot. We have a new, not a new, but we have another thing in seismic attributes that's very, very important. Using seismic attributes with a spectral decomposition. Spectral decomposition trying to decompose the seismic frequency into the all of its frequencies component, then looking at each single frequency in order to identify the features that are found in the subsurface structures. And all the each frequency may yield an information that differ then from another frequency that may yield another frequency, another information that differ from the other frequency. So a lot of frequencies, a lot of seismic features that we can find when we are composing that frequencies. When you find the best 3 frequency slices, you can use these frequency slices in order to combine these 3 slices in order to get with the spectral decomposition. The spectral decomposition, we are using here RGB colors: blue, green, red. The blue expresses the 16 hertz, while the green expresses 26 hertz, and the red color represents 36 hertz amplitude. So it can combine all the benefits from the different 3 frequencies in order to show you all your features of your data. Another channel that will not be appeared in the last slide maybe appear here. You cannot find details here in this slide, or cannot find these details. And when we move to combining or blending our 3 the seismic data, we can find this information here. So spectral decomposition is a very, very good seismic attribute that we can use to identify the lateral variation of our subsurface geology in order to identify it, and we can target it in our drilling. And of course, the seismic attributes may to take the very crucial thing to take in your consideration where the top of the horizon that you are picking. If you have the same 2 seismic section and you are trying to pick in the upper section, you are trying to pick the trough itself, okay, the black trough. Then you have here a channel, and this channel you are trying to follow this channel, and this you are going down, then going up, and then continue your interpretation. On the other section, the lower section, you are using here the interpretation, the same black, the same black reflector. Then you are trying to come to this channel, then you cross the channel and don't go with the channel down and up. You cross the channel. So this may yield different information. This you can say that this is a very small effect on our data, but of course it will yield 2 different scenarios or 2 different images of the data, and this is the images that are yields using the 2 data. You have here the data that you are using. You are crossing the channel, so you cannot image the channel clearly. But when you are going down and going up, then with the channel, you can find this on the map, the attribute map for this channel. The channel and at the map view, directing from here to there, then trying to continue to that trend. Okay, so this is very important to know. The interpretation of seismic data may affect your data and may affect the results you have. Of course, the small thing that you are may not take into consideration. This is very, very important, and they may yield a lot of information that you may interpret this. You do not have any channel in this area, but in reality, you have a channel here, and we can identify it clearly. But the 2 different methods of interpretation yields 2 different images of your channel. So it's very, very important to know the interpretation, the technique that you use in your data to interpret it. Moving to the the seismic resolution. The seismic resolution is very, very important in your data, and every interpreter should know the resolution of the data that he worked on, because sometimes you are trying to pick your reflector, then the reflector differ from the differ, and you cannot continue to find your reservoir. Is it you can find a lot of amplitudes, and the amplitudes, is it represent hydrocarbon or represent a phenomena of tuning? The tuning phenomena is very important to know, because the tuning phenomena may lead you to interpret the horizon where the horizon cannot appear in your data. So it's very important to know the resolution of your data. And the vertical resolution is known to be the fourth of the wavelengths. So if you have the thickness of your reservoir, which is less than the fourth of the wavelengths that you are using in your seismic data, you cannot find the top after that. We are here have a good thickness, so we can identify the top and the base of reservoir. Then this is the resulted seismic trace for the top and base reservoir. After that, we have the thickness decreases. Then the thickness decreases till we have here an interference. The interference here is constructive interference. Then the constructive interference gives you a bigger peak, and this bigger peak not related to geology in reality, but it's related to the constructive interference. The difference of the thickness, the decrease in thickness may arise this. So after that, the thickness decrease, then the peak or the trough increase, so the amplitude increase, but it's not for a real data. Then we are moving to from the constructive interference, and suddenly you will find the destructive interference. And this at this moment you have two possible answers. The first answer that you have your reservoir. You have here your reservoir, but you cannot resolve the top and base of the reservoir. And the second answer is you may not have any reservoir anymore here after that area. So it's very important to know, you are tracing a reservoir which is resolved by your seismic data or not. And this is not only in the thickness or the vertical resolution, it also may be applied on the horizontal resolution. If you have a narrow horst here, and this narrow horst have your reservoir, it may represent a good trap. So if this width of the width of this horst is very small and smaller than the half of the wavelengths, you cannot image this horst, and you will not find any horst in your seismic data. And if you are trying to find stratigraphic traps, and you have two or more channels, and the space between the two channels is less than the half of the wavelengths, because it's a horizontal resolution, you cannot identify that you have two different sand bodies. You will find it as a one sand body on the seismic data. The seismic cannot resolve the two bodies. It will resolve one body and have this as a one body. So it's very important to know the resolution. The resolution is very, very effective parameter in the seismic data, and your details cannot be clear on your seismic data if you used in acquisition frequency range that not enough to capture the data or the details that you are trying to find. So this is an important factor which may be found in the seismic acquisition. You cannot acquire data after you acquire your data, and you cannot trying to change the frequency range that you are using. So it's very important. You pay a lot of money in order to acquire seismic acquisition. Then you come up with seismic data resolution. The resolution is not good, and a poor seismic resolution you cannot find your seismic, cannot find your details. It will not help you in your development stage. So it's a very crucial step to find a good frequency to start your acquisition with. But if you have a lot of you have a seismic data now, and the seismic data that you are having have a low frequency. Could we improve this frequency? It's very helpful to increase or trying to enhance the frequency of your seismic data. And the answer is yes, we can improve the resolution of the data that we have. If we do not have anything except this data, we can try to improve the resolution that we have. And this is an example for the seismic data that was enhanced using different seismic attributes. And to the left is original seismic data that was acquired by the acquisition, and to the middle, another side, the same section with the same scale, but there was enhanced seismic data. And then the other section to the right is enhanced also using another different seismic attributes. The middle section was enhanced by using second derivative attributes. And the second one and the third one is enhanced by using spectral blueing. Spectral blueing, trying to hiring the blue color, which represent the high frequency, so you can increase your seismic resolution. Note this: you have here the baked reflector in green. We have here the data here. This is the original seismic tube. We are trying to find a relation and what is the frequency that was improved. Trying to look at this package. Looking to this package, two reflectors, the two red reflectors here. We have the same two red reflectors here, but we have a new reflector, and not a new reflector. Is a feature that appeared here, occurred in this section as a result of enhancing this resolution. And looking to this, we have this feature trying to express itself, but not enough to have a good reflector like this here. So we have here a good seismic enhancement using the second derivative attributes. Another thing in this section, we can find, we have here this reflector. Trying to find this reflector. The reflector here we have two peaks that trying to, from here, have two peaks, then trying to tuning effect happen here. But when we trying to find this feature in this section, we have two different peaks here, two different red peaks found here. And then we are trying to find a more, a better clarifying these two different, but not enough as this section. So the answer is yes, we can improve the seismic data resolution to some extent, of course, to some extent, using our seismic attributes. And this is trials, and the trials need to be applying a lot of parameters and trying to find the spectrum of your seismic data, all of this depending on the spectrum of your seismic data. And then after scanning your spectrum of seismic data, trying to enhance or increase the resolution or the spectrum at the high zone of frequency. So to summarize our presentation, you are trying to we will summarize with the generalized seismic interpretation workflow that you can use in your data and applying for any data you have in seismic data in order to come up with the results that you want. You have a data, so you are gathering the data and QC. Gathering the data and the QC comprises the data and the reports that of seismic data. You have a seismic data and you have a velocity cube. So I have all of the data you have. You have a seismic data, the pre-stack data, or post-stack only, or post-stack seismic data only. If you have a pre-stack data, which format you have? This is a gathers, or you have the gathers, or you have a partial angle stacks, you have angle stacks. In which domain? You have a time in you have the in time or depth. And if you have a velocity cube, is it a depth cube velocity or time domain velocity? If in depth, does it in feet or meter? All of this in the data included in data gathering and QC. And this is a very crucial steps to know, and very important to know the parameters and the cubes that you are dealing with. Then you are moving to the well data editing and QC. You are trying to use the well data like sonic and density. You are in seismic data, we are dealing with the sonic and density logs. It's very important to know a lot of information about density and the sonic logs, because you are using this in generating a well, generating a synthetic and acquiring well to seismic tie. The well to seismic tie will help you to identify which reflector in your seismic data represent which top geological top in your logs that you are interpreting in your logs. So then after you identify your top, you can make your seismic data, or you can make some conditioning of seismic data. If you have a low frequency and you do not have a good seismic cube, and you are trying to take the benefits as most as you can from your seismic data, you can run some seismic conditioning steps in order to enhance your seismic data and increase the frequency a little bit, then interpreting the seismic data in order to find your reservoir and tracking your reservoir. Then after picking your horizon, you can come up with the horizon, then fault interpretation, the fault tracking interpretation, can be used with the horizon in order to build a structural framework. Structural framework give you 3D insight for your area, and then you can use the seismic attributes in order to ensure that these horizon are found in this area, and you have these faults here, and we can confirm the presence of faults or or absence by using seismic attributes, which could help you to modify your fault and horizon interpretation. Then moving to structural framework. Then after finishing the structural framework, you should take your data, which was in time domain, and convert it into depth using the velocity data and velocity analysis. You can, and the velocity data and velocity analysis are depending on the data that you have. All the velocity information can be used using the a lot of things, or a lot of information, a lot of you have check shots only, you have a velocity cube, you have a stacking velocity, you have interval or average velocity cube. All of this information is very important to know, and this yields, of course, all of this yields different images of subsurface. So if you have a lot of information, you can run uncertainty analysis. Then you can identify your depth of the horizon with the uncertainty. So it will give you a stochastic estimation of your horizons and your reservoir. So this is the last step in the seismic interpretation workflow, and this is a conventional interpretation. But you know that we have a lot of things that have a new, not a new trends, but the very common, which is called, all of what we are mentioned here is a conventional interpretation or qualitative interpretation. You can move to the quantitative interpretation. The quantitative interpretation may help you to find a lot of information that you cannot find in this workflow, the ordinary workflow. The quantitative interpretation may help you to identify the reservoir, saturation, porosity, and character. You can characterize your reservoir and find a lot of information inside your seismic data, and use a lot of data or a lot of information inside the seismic data by applying seismic inversion and rock physics where you can also apply the neural network in order to predicting the hydrocarbon saturation using the seismic and well logs data. So it's very wide use for the seismic data. You can use seismic data in the quantitative or qualitative interpretation. All of this depending on what the data you have and what the knowledge you have and what things you know or you need to know, what things you need to know, and in which time, in how much time. So all of this can take a lot of things, a lot of time to do these workflows. Every workflow have different steps, have different data required, have different conditioning for seismic data, and all of things you need to know is what the information you need to extract, in which time, and how, and the knowledge that required for this. And thank you for attendance. Thank you for your listening. And I have you have an opportunity to have. If you have any questions, I will listen to your question and try to answer all of these questions.
Thank you, Dr. Ahmed, for this interesting session. Actually, it was very, very interesting, and I think that all the attendees enjoyed your explanation and discussion. Actually, we have a question here. The first question, can you explain how can we doing spectral blueing? I think this attribute increases frequency bandwidth.
Yeah, of course, and we are mentioned this spectral blueing here in this slide. This is the last this is the section that on your right. The spectral blueing using the seismic data and using the frequency spectrum of the well data in order to enhance the data that you have, enhance the seismic data that you have. So it's called spectral blueing. Spectral from spectrum and bluing from blue, the blue color. When we are trying we are trying to categorize the colors RGB. So the red for the low frequency and G for mid frequency and the blue for the higher frequency. So we are trying to blowing and hiring or increasing the high frequency range in the seismic data in order to come up with a good enhancement for seismic. So we are using the seismic, a combination of seismic and the well data. And of course, a lot of steps we can include, but I think time we cannot show it in detail. But the most critical point in this, to use the data from your wells. Okay, the spectrum of your well logs. You are taking the seismic cube, then they have a sonic log and density log. After you have the sonic and density logs, you are trying to come up with the acoustic impedance log by multiply the sonic and density. You have acoustic impedance. The acoustic impedance for all wells in your area, taking a spectrum for this log, then combine with the seismic in order to come up with the spectral blueing cube.
Okay, thank you, Dr. Ahmed. We have another question. In 3D seismic, if I have full azimuth acquisition, can I get good seismic image wherever receiver distance I have?
Of course, as we mentioned before, the distance of the receivers, of course, play an important role in seismic. So if you are acquiring a full azimuth seismic acquisition and you have a very big distance between your receivers, of course, you will not record all the information that reflected from the subsurface. So your target is to record as much as you can from the reflected seismic from the subsurface, which represent the reality that come from the subsurface.
Okay, thank you, Dr. Ahmed. I think that the time is very, very tight now, and we have many questions. So thanks for everyone that asked his question, and thanks for everyone that attended our session today. Also, the big thanks is for you, Dr. Ahmad, for this interesting. We have very, very good, good feedback about this session. I think that it was one of the most interesting sessions that Reservoir Solutions conducted. So thank you again for your effort and time allowing this session.
Thank you for your attendance. Thank you for Reservoir Solution. And of course, Seismic have a lot of, applications and a lot of things we cannot deliver in one lecture. Of course, a lot of things we can deliver, and we'll try to design a lot of webinars, of course, in the coming sessions, inshallah.
Inshallah. Thank you again, and thank you for everyone.
Okay, thank you.
Thank you.